We're going to look at solving equations by factoring. So first, a few equations we're going to look at. The first one is what would be called a linear equation. X is just to the first power. So if I'm solving 2x equals 100, I undo multiplying x by 2 by dividing both sides by 2, and I have x isolated right away. X is by itself, and I can see that x is 50, 100 over 2. Now, the second equation, notice that I have x squared. And so in this case, I'm actually going to end up with two answers for x. And I'm going to arrive at them in a very similar way. I'm going to perform inverse operations until I can get x all alone. So I'm going to undo adding 5 by subtracting 5 from both sides. So now I have x squared is 100. Now here you've really got to think about this, because everybody is quick to say 10. 10 squared is 100, but there are two numbers that when squared will give you 100. 10 squared is 100, and also negative 10 squared, because negative 10 times negative 10 is 100. And so we're still isolating x, and to do that I need to perform the inverse of squaring, which is square rooting. So when I square root both sides, I actually need to take plus or minus. So this symbol, a plus with the minus below it, is read plus or minus. So that gets rid of that. Inverse operation. So here I get x equals plus or minus 10. Positive 10 or negative 10. So, in both of these cases, number 1 and number 2, we were able to isolate x to get x all alone by performing inverse operations. Now, the difference here on this third example is that I have an x squared and an x to the first power. So they are not like terms, I can't combine them, nor can I isolate x because x is occurring in two different places. And so that is where we're going to start looking at solving by factoring. So in this case, what I would do, we'll go ahead and show you, is I would factor this. So first I'd look for a common factor. There's not one. So I would go ahead and see if I can write this as a product of binomials. So I think about what times what would give me x squared, x times x. And I think about all the things I can multiply to get positive 6 when I multiply this term by this term. So it could be 6 times 1, negative 6 times negative 1, 2 times 3, or negative 2 times negative 3. These all have a product of positive 6, but I want to combine like terms to get negative 5, negative 5x. So I know it's going to be minus 2 and minus 3. And so now that I've factored it, I can solve it. So see here, instead of having an equation with an x squared and an x term, I have two smaller equations I can now set up and solve for x in each one. I'm going to set this equal to 0. I'd add 2 to both sides to get x all alone, and I get x equals 2. On this equation here, x minus 3, I'd set it equal to 0. I would add 3 to both sides to isolate x. That would eliminate that, and I would get x is 3. So here are my two answers. X is 2, and x is 3, and sometimes that is written as a solution set, so you have it in a bracket like this. So you would get x equals 2, comma 3. So I got two answers. Here I had that x squared. Okay, so now a little more detail and several more examples about solving for factoring. So the first thing I want to point out is the difference in an equation versus an expression. So if I just had x squared minus 5x plus 6, if that is just an expression, I can't solve for x. When it's set equal to something, say 0 in this case, then it becomes an equation and I can actually solve for x. So here we have something that is already factored. So if it said to solve the equation, what I could do is set each individual factor here equal to 0 and solve for x. So this is the benefit, one of the benefits anyway, of factoring. It allows us to solve quadratic equations much easier. So in each case, I'm going to isolate x. Here I'll do that by subtracting 7 from both sides. So I get x is -7. And here I'll do that by adding 4 to both sides. And here I get x is 4. So I get x equals -7 and 4. So that would be my solution set. Sorry about the brackets here. -7 and 4. Okay, some more examples. So here I have a quadratic equation. I have x squared. Here I can solve this by factoring, or I can solve it without factoring. But in this case, I'm going to solve it by factoring for the practice. So this, upon first glance, might not look factorable, but it is because it is a difference of squares. It is a difference, a subtraction, of two things that are perfect squares. So x squared and this is 6 squared. So that was kind of one of those you just had to memorize. So when you factor this, you get x plus 6, x minus 6 equals 0. And now I can set each one of those binomials individually, set each of those equal to 0 and solve for x. So I'd set this equal to 0, solve for x. Then I would set the next equal to 0 and solve for x. So here when I do that, I'd subtract 6 from both sides. I'd get x is -6. Here I would add 6 to both sides. That would give me x equals +6. So I could write that in brackets as a solution set. And another way you might see this is x equals ±6, which is a shorthand way of saying +6 or -6. Okay, and another example, and hopefully you've noticed, maybe not, that in each of these examples that we've done so far, so here it was set equal to 0. Here it was set equal to 0. Here we had it set equal to 0. So that is a prerequisite to solving by factoring. It needs to be set equal to 0 at first. So let's say that it wasn't set equal to 0. Let's say, for example, you had x squared minus 7x equals -6. Your first job to do would be to get it equal to 0 over here. So I would do that by moving the 6 and then getting this equation. So if it's not set equal to 0, you want to do that first. Then I'm going to see if I can solve for x by factoring. I can't just get x alone by performing inverse operations, because here I have x squared and here I have x to the first power, so I need a little help. So I'm going to try to see if there's a common factor between the three terms. There is not. So now I'm going to solve by reverse foiling here. So I think about what I can multiply times itself to get x squared. That would be x times x. Since this number is positive, I know it's either a positive times a positive or a negative times a negative. And I know it's a negative times a negative because of this. So then I think about all the things I could multiply to get +6. So I could do +2 times +3, -2 times -3, +6 times +1, or -6 times -1. So all of those have a product. They multiply to get +6, but I want the ones that combine like terms to give me -7. So I know it's -6 minus 1. And now I can set each of these individual factors equal to 0 and solve quite easily. So if I set x minus 6 equal to 0, and then I set x minus 1 equal to 0, Here I would just add 6 to isolate x to get it alone, and I get x equals 6. So here I get x equals 6, and in the second factor here I would add 1 to get x is 1. So it really doesn't matter what order I write my solutions. I usually prefer to write the lesser one first. It doesn't necessarily matter. So here are my two solutions. Okay, we'll look at another example. So in this example, I can actually solve this without factoring. And I know that because I have an x squared term, but I don't also have an x term. I don't have an x to the first power here. So I can actually isolate x without having to factor. So I want to do that both ways for you. So one way I'm going to do it by factoring, and then I will show you how to do it by just performing inverse operations. So here's my first. Okay, so for the first example, and for the second example, second way I do it, you can see that you have a common factor here of 3. So if I were to factor out a 3, I'm going to try to solve this by factoring, by first factoring out a 3. So I get 3 times x squared minus 4 equals 0. And so now when I factor out that 3, I can see that what I have in parentheses here is another difference of squares here. Perfect square, so that gives me x plus 2, x minus 2. And then I'd set that equal to 0. And so I would first set each of these now equal to 0 to solve for x. So 3 equal to 0, that's not a thing. That doesn't make sense. 3 will never equal 0. There's no variable there. That doesn't give me a solution. But if I set x plus 2 equal to 0, and I set x minus 2 equal to 0, I'm going to get x equals negative 2 and x equals positive 2. So I'd solved both of those. I get x equals negative 2, x equals positive 2, also known as plus or minus 2. So this one I could have solved without factoring, and I know that because there's an x squared term but not an x term as well. So I could have isolated x in this case. I could have added 12 to both sides to get rid of that. So now I get 3x squared equals 12. Then I could undo multiplying x by 3 by dividing both sides by 3, which gives me x squared equals 4. And then to undo squaring x, the inverse of squaring is square rooting. If I do it to one side, I do it to both. Those cancel out, and I get x equals plus or minus 2. So a downfall of solving it this way is people very often forget that negative 2 also. 2 squared is 4, but negative 2 squared would also be 4. So I get the same answers either way. Okay, just a couple more examples here. So here, if I solve this one by factoring, notice it's already equal to 0, so that's good. If it's not already equal to 0, you need to make it equal to 0. Oops, sorry about that. So I need to first check to see if all three of those terms have a common factor. They do not. So then I think about what I could multiply times itself to get x squared. It's x times x. I think about all the things I can multiply to get negative 14. Maybe 7 times negative 2, or negative 7 times positive 2, and so on. Until I see the factors that combine to give me positive 5. So I know it's going to be plus 7 minus 2. So when I set each individual factor equal to 0, set this one equal to 0, set this one equal to 0. Now I have a much easier time isolating x here. So I get x is negative 7. And when I solve this small equation here, add 2, I get x is 2. So I get two answers. which is what I would expect. And that problem is complete. So notice in this problem, because it does happen occasionally, in this problem, you have a common factor. So you have a 2 that is a common factor in all of these terms. So if you factor out a 2 first, that would give me x squared minus 4x minus 21 equals 0. Again, that is good that it's equal to 0. If it's not, you'd have to move something. So I'm going to keep the 2, and then I'm going to factor what's in the parentheses here. So I will factor that one a little faster than I have been. I know it's a positive times a negative. Factors of negative 21 is going to be negative 7 and 3. So now if I set each one of these factors equal to 0, that's just a 2. So setting 2 equal to 0 doesn't make sense. If there were an x there, that would make sense, but there's not. This is going to give me negative 3 when I set it equal to 0. And this is going to give me positive 7. So I went a little faster there. So I get x equals negative 3 and 7. So here we have a binomial instead of a trinomial. We just have 2 terms here. And so again, I'm solving. It's equal to 0, so it means I'm trying to solve for x. So when I go to factor this, I notice both terms have a common factor. They both have an x. So when I factor that x out, I get x times x minus 1 equals 0. So I just factored out the greatest common factor. So then I'm going to set each factor equal to 0. So I set x equal to 0. And then I set x minus 1 equal to 0. So this, when I set this x equal to 0, that gives me my first solution. X can equal 0, so there's my first solution. For the second part, I add 1 to both sides to isolate x, and I get x is 1. So I get x equals 0 and x equals 1. Okay, one last example here. So here we have a trinomial, and notice that my leading coefficient here is not a 1. Sorry about the noise. So here I have that 2, and I cannot factor it out. So here is where I believe most of us were factoring these by grouping. So I'm still trying to solve. So a trick to do that is to take this leading coefficient and multiply it by that last term. So I get 30. So then I'm going to use that 30, and I'm going to think about all the factors of 30 that can combine to give me 13. So right off the bat, I notice that 10 times 3 is 30, and I can combine it to get 13. So I'm going to rewrite this middle term. So I'm going to keep the 2x squared, but I'm going to rewrite plus 13x using the 10x and the 3x. So I'm going to do plus 10x plus 3x. So notice I haven't really changed this trinomial. I'm just changing the way it looks. And then also notice, just kind of a reminder, I wrote the 10 first because I noticed it had a common factor with 2. And I wrote the 3 next because it had a common factor with 15. So I was strategic by writing 10 then 3 and not the reverse. So now I'm going to factor by grouping. So these 2 terms have a common factor. So notice these 2 terms have a 2 in common. Oops, sorry here, I forgot to write my x with the 10. I knew something looked wrong. So here, these 2 factors have a 2x in common. Cleaning up my mess here. So those 2 factors had a 2x in common. So I'm going to factor out that 2x. And when I factor out the 2x, I'm left with x plus 5. Then I have that plus sign in the middle I'll bring down. And so now I'm going to look at this group here and notice that their common factor, the greatest common factor here is 3. When I factor out a 3, I get 3, then x plus 5. So this is a review of factoring trinomials when the leading coefficient isn't 1. So then the way I write this would be the 2x plus 3 together, then the x plus 5 together. And that part was all actually review. That was factoring. Now we're solving by factoring. So now that I've factored it, I'm going to set each factor equal to 0 to get my solution. So I do 2x plus 3 equals 0. And then I'm going to set x plus 5 equal to 0 to get my two solutions. So for this first one, I'm going to subtract 3. I'm trying to get x all alone. I'm going to subtract 3. So I get 2x is negative 3. I'm going to undo multiplying x by 2 by dividing by 2. So I'm left with x equals negative 3 halves. It is perfectly okay to just leave the fraction. For this second equation here, I would subtract 5 from both sides, and then I would get x equals negative 5. And I could write those in bracket as a solution set. I could write them together. So one last thing I wanted to just kind of remind you of is making sure that you get it set equal to 0 first. So for example, if you had like x squared plus 5x equals, let's say, negative 6. So if you were to solve this by factoring, if you were doing that, I would first need to make sure that this side was 0. So I would take x squared plus 5x plus 6. Notice it is not a like term, so I'm not combining. And then that would just give me 0. So the first step is to make sure it equals 0. Again, sorry about all the background noise today. Okay, let me know if you have any questions.